We shall do some more problems on Levi Civita symbol, which are extremely useful and important. Find R cross P 3. That is, we have to find the third component of the product of position vector and the momentum vector. Start with what is given, and using Levi Civita symbol we can expand it. This is the third component, so the index 3 appears here, and the sum is over j and k, which means it will be rj and pk. Obviously j cannot be 3, and so is k, because then Levi Civita symbol will give values which are 0. So these correspond to surviving terms or non-zero terms, and therefore j and k takes values 1 and 2, which are the remaining indices, because 3 occurs here. And further, j cannot be equal to k, because Levi Civita symbol is 0 for identical indices. And therefore let us expand and write, let j be 1, so k is 2, and then we can take it to 1, so that r is 2 now, and k is 1. Now epsilon 3 1 2 is plus 1, and epsilon 3 2 1, it being anticyclic, is minus 1. So what we get is r1 p2 minus r2 p1. Clearly, therefore, we can rewrite it as z component. R1 is x, p2 is py, r2 is y, and p1 is px. And this is Lz, where vector L is the angular momentum, so it can also be written as vector L of z component. In the next problem, we have to establish this identity or this relation. A dot B cross C can be written as B dot C cross A. This can again be written as C dot A cross B. So let us solve this problem. We start with A dot B cross C, breaking it into component form. Now we can dissolve B cross C and write it as so this is what we get. Now to get to this form, we have to write B first, then C, then A, and these are scalar quantities, so we can interchange their order. So let us write this Bj first, then Ck, and finally Ai. Now here we have Ckai, which means the last two indices should be Ki for it to be presented as C cross A. So let us write it as, and then as a further shuffle of I and K gives us JKI, and the negative sign that comes out neutralizes this negative sign, so we have epsilon JKI, and here we have BJ CKAI, and this is equal to Bj, and this is nothing but the jth component of C cross A. And this is the dot product of B and C cross A. So we have proved that A dot B cross C is equal to B dot C cross A, as wanted in the question. We will now show that A dot B cross C is equal to C dot A cross B, and this means we have to write C first. So let us start with this expression. So CK, then we have to write A. So it is AI, and finally B. Now here we have AIBJ, which means this Levi Civita symbol should involve IJ as the second and third indices. And this means K has to be brought to this side. So this is minus, let us bring K to the second position first at the cost of this negative sign. So it is IKJ. And then we have epsilon. Let us interchange IK, Kij, and the negative sign that comes out will neutralize this negative sign. So this is what we end up with. So we have here AI, BJ, here we have CK, and this is nothing but the K component of A cross B, and this is the dot product of C and A cross B vector. So we have proved that C dot A cross B is also equal to A dot B cross C. So for cyclic occurrence of ABC, the scalar triple product is invariant. This we have shown. So we can write that scalar triple product is invariant under cyclic permutation of vectors A, B, and C. In the next problem, we will prove another relation, namely A cross B dot C cross D. This we have to show to be equal to A dot C into B dot D minus A dot D into B dot C. And let us get started. Let us start with the left hand side. Let us consider the ith component, and repeated index means the summation is over I, and now A cross B can be dissolved. So it will be I, J, K, A, J, B, K, and ith component of C cross D will be, let us use indices, say M and N. So what we get is now here we have I, here also we have I, and we can use the standard formula. This can be written as, so it is Jm, and this is Kn, and then Jn and Km. So this is what we get. So let us dissolve it. Obviously, the first term survives only if M equal to J and if N equal to K. because of the existence of these two Kronecker deltas. And similarly, the second term will survive only if n equal to j and only if m equal to k, as indicated by the presence of these two Kronecker deltas. So this becomes aj, bk, c, j and dk minus aj, bk, c, k and dj. Now writing terms with similar indices, we have aj, cj and here we have bk, dk, and we can club terms with similar indices, and so we have aj, dj and here we have bk, ck, and this is nothing but a dot c and this is b dot d, this is a dot d and this is b dot c. So we have proved this relation. Let us prove another very important relation, which is a cross b cross c is equal to this is a relation of paramount importance and is widely used in physics, which we shall prove now. So the answer is, let us start with the ith component of left hand side, which is, and it will be aj, b cross c, kth component, so that the sum is over j and k. Now it is the turn of writing the component of b cross c explicitly. So it is say kth component. Let us use Lm as indices. We will have Bl, Cm, and let us write the two Levi Civita symbols together, and we have Aj, Bl, Cm. So we have product of two Levi Civita symbols, and to apply the formula, let us translate k to the rightmost side. So this Levi Civita symbol can be written as minus epsilon L K M, where we interchanged k and L, and a further interchange of k and m makes it positive, and we will have L M K, and we are already having I J K, and we note that now we have k here, and we can apply the formulae. IL and then JM, and then we will have IM and then JL. We dissolve it into two terms. The first term survives only for m equal to j because of this Kronecker delta, and L equal to I because of this Kronecker delta, while the second term will be non-zero only for m equal to I as evident from this Kronecker delta, and for L equal to j as evident from this Kronecker delta. So we are left with Aj, Bl equal to I and C m equal to j minus Aj, Bl equal to j and C m equal to I. Collecting the terms with same indices, so we have Aj, Cj, Bi minus Aj, Bj, Ci, and this is nothing but A dot C, and this is A dot B, and this is the ith component, the left hand side of which is this one which we started with, and this holds for all the components, that is for any I. So we can write and since this is scalar, this can be placed anywhere. So this relation has been proved. We come to the next problem, according to which we have to prove that this into vector C minus this into vector D. Let us consider the left hand side. In fact, we will be considering the ith component of the left hand side. So this gives us ith component. So the first index is I. So it will be jth component of the first vector, and it will be kth component for the second vector. Now let us dissolve these two. Jth component, so the first index is j. Let us sum over, say, indices p and q. So it will be AP, BQ, and then this is a kth component, and therefore it is to be summed over L and M. So this is how we write component of cross products. So here we have product of three Levi Civita symbols. Let us now have a look at the right hand side, which we are to prove, and we see that A cross B occurs in both the terms, which means component of A cross B, say the jth component, will be common to both the terms. So therefore let us rewrite it as, let us write this one in the second spot. So this one, or rather this combination of terms, will be common to both the terms on the right hand side, which we will prove. So we will keep them intact and deal with or focus our attention to the product of these two Levi Civita symbols. Now here we have K and here we have K. Let us switch this K to the leftmost side. Let us interchange the indices J and K at the cost of a negative sign, and then take K to the leftmost side to end up with K I J. So with this we have this being kept together as promised. We find that K is here, K is here, so we can write, instead of this product of two Levi Civita symbols, so it will be IL JM and then I M and J L. So we split it into two terms. So this is what we have, and note that this combination is together, from which we will get this part A cross B in the two terms. From the first term, the non-zero surviving terms correspond to I equal to L and to J equal to M, and in the second term it will be I equal to M and J equal to L. All other terms will be 0 because of the presence of Kronecker deltas. So that common part, and then we have C. Instead of L, let us write I. Instead of M, we have to write J. This is the common portion, and then instead of L, let us write J. Instead of M, we have to write I. And this is the common portion, which can be written as A cross B, the jth term. The jth term. So this can be written as, let us write dj first. They're scalars, they can be placed in any order. So this is what we have, minus, here we have, let us write Cj first, or we have dot product of these two vectors. Here it will be dot product of vector C and vector A cross B. This is obviously the ith component which we have obtained in the right hand side, which matches the ith component of the left hand side. So in general we have this relation, and let us write it. So this gives us the left hand side this is equal to the right hand side. A problem on Poisson bracket. For details on Poisson bracket, you have to refer to the video on Poisson bracket. We have to find the value of where this bracket is called the Poisson bracket. L stands for orbital angular momentum, and it is given that Lj, the Poisson bracket value is I, J, K, L, K. So let us start with the solution of the problem. This is what we are given. This is the left hand side. Let us consider the jth component, and therefore let us rewrite it as now use this relation, and we can rewrite it as epsilon ji, and a third index let us write k lk. So we can write it as let us take Levi Civita symbol outside the Poisson bracket, and we are left with the value of which is let us write it p. Here p is the dummy index chosen. Therefore let us note that here we have ik and here we have ki. So let us manipulate a bit to bring this one in the same form, interchanging the indices I and k, and now p can be brought to this side by two interchanges, and what we get is, therefore, because p first comes here, one negative sign comes out, and then that p goes here, that is to the leftmost side, and another negative will come, and so this negative will be preserved. So this is what we get. This negative sign is here. We clearly have identical indices I and k, and this is twice Kronecker delta jp, as we proved in a previous problem, and this gives us summing over p, and only j equal to p term survives, so lp will be replaced by lj. Clearly this is the jth component, the right hand side, the left hand side being this one, which also is the jth component, because here we have lj, here also we have lj. So in general, therefore, let us write with vector L, and then we'll have this relation. Writing vectorially, we have so this is the required value. Let us do another problem. In this problem, this vector triple product now start with the left hand side. Let us consider the ith component. Ith component, so the index I is here. A cross B jth component, ck. And now this cross product is dissolved. Jth component, so it is AP BQ CK. So we have two Levi Civita symbols. Now here we have J index, here we have J index, the common index, but this is the first index and this is the second index. So let us bring uniformity in them. So this can be rewritten as interchanging the first and the second index. So what we have is now this is J index, this is J index, so this is the common index, and let us apply the formula. Kronecker delta IP into Kronecker delta KQ minus Kronecker delta IQ into Kronecker delta KP. This negative sign is written here. Let us absorb this negative sign inside, and so we have to write the second term first. So it is and the first term let us write here. First term will survive only if I is equal to Q and K equal to P, while the second term survives only for I equal to P and K equal to Q. This gives us AP B Q. Instead of Q let us write I, CK. Instead of K let us write P, minus instead of P let us write I, instead of Q let us write K into CK. So rearranging, and this is the dot product of A and C. This is the dot product of B and C. And in vectorial form we can write, therefore the left hand side becomes and the right hand side is this one. That incorporates all the components, and this is what we were required to prove. Alternately, we can write in this way, because A dot C and B dot C are scalars, they can be placed anywhere. So we have proved this very standard relation for a vector triple product, and derivation of it requires use of Levi Civita symbol.